so this is magnetic fields. So first of all, we need to understand the concepts of magnetic field. First point, magnetic field is a region in which a magnet, a wire carrying current, or a moving charge experiences a force. Okay, so that means you have a magnet, you have a wire carrying current, or it can be a moving charge. So when magnet and the current interact, then at the end it produces a force. Okay, it produces a force. They are trying to say something like that. So imagine that we have a magnet. Normally we use B to represent magnet, B. We have a current, and then at the end there is a force that is produced because of the interaction between the magnet and the current. Okay, so of course this current can be a wire carrying current, a straight conductor for example, or a coil. Okay, so or it can also be a moving charge, so carrying current as well if it's moving. Okay, so we look at the next part first. Can be produced by current carrying conductor. Okay, so this second point, right, they are trying to say, if you want to produce magnetic field, there are two ways. The first way is use current carrying conductor. Where we will come to it very soon at 9.3. We call that electromagnetism. Okay, current carrying conductor will produce a magnetic field through electromagnet. Electromagnet is temporary magnet. As you try to imagine, if current is not there, then the magnetic field will just disappear. The second types of magnetic field is where it is produced by a permanent magnet. So permanent magnets, of course, the word's permanent, that means it is there all the time. So it is produced by a magnetic bar, something like this. A magnetic bar produce a magnetic field. Okay, and it is permanent, so the magnetic field is over there all the time. Okay, so now let's move on. Okay, so 9.1, they tell us two different concepts. So the first concept is B plus I produces force. The second concept is who can produce magnetic field. So these two can produce magnetic field. So they tell us two different concepts. Now 9.2, representing magnetic fields. Okay, so magnetic field due to permanent magnet. Okay, so it looks like this. We have a north pole. For the permanent magnet, we have the south pole. North pole is where the magnetic force come out. Okay, and south pole is where the magnetic force go in. At the south pole. Okay, now let's see the next point. Yeah, magnetic field lines come out of the north pole and go into the south pole. So as you can see here, come out from the north pole and then go into the south pole. Okay, so what is coming out actually? So, and what is going in? So we need to know about that. The arrow should represent something, right? So it is written at the next point. Directions of field line at any point in the field shows the direction of the force that a free magnetic north pole would experience. So they're trying to say that if you put a north pole here, then it will experience a force which we follow this arrow. you know, north and north, they will repel, right? So this arrow represent that. Okay, this arrow represent that the North Pole will experience repulsive force. Okay, so that means this arrow, right, represent what happens to the North Pole. The North Pole will be repelled by this. Okay, so likewise, if you put a North Pole on this side, so the arrow over here means what happened to the North Pole. So the North Pole will be attracted to the South Pole. So that the arrow means that. Okay, now let's move on. The next point, this point. Field is strongest where field lines closest together. So this should be easy. Where around here it is strong because you see many field lines, and somewhere around here you can see this is weak. As you can see, no or not many lines here. This particular part will be weak, and here will be strong. Okay. When you see many lines, it is strong. Okay, now let's move on. 9.3. 9.3, electromagnetisms. So let's look at this point. Electromagnetisms. Just now, I already mentioned a little bit. It is the current carrying conductor that produce electromagnet. Okay, so current carrying conductor. So let's see here. The strength of magnetic field can be increased by increasing the current. So this should be logic. Imagine that if the current carrying a greater, the conductor carrying a greater current, and then the electromagnet should be stronger. Okay, next point. Increasing the number of turns per unit length of solenoid. This will increase the electromagnet, the strength of the electromagnet as well. So this is for solenoid. You have to know that solenoid is where they put the wire into a coil, something like this. So if there are more coil, of course the electromagnet should be stronger. So you increase the number of turns per unit length. That means, for example, per meter. Increase the number of turns per meter will make the electromagnet stronger. And third point, using soft iron core within solenoid. So what happened here is you put a soft iron core. So what is soft iron core? It is basically a pure iron. So imagine something like this. You put a soft iron core in between. Okay, then this soft iron core will make the electromagnet a stronger magnet. Okay, now these are the three ways to increase the strength of magnetic field. And then now right hand grip rule. Right hand grip rule. So right hand grip rule is used in this way. So first you need to know the middle of the diagram is actually the current, the straight wire. So the current is pointing upwards. Yeah, the current is pointing upwards, and then right hand grip rule is used in this way. You have to grip your straight wire by using the four fingers, and then your thumb point upwards, following the direction of the current, and the four finger that turn in anti-clockwise direction is actually representing the magnetic field. Yeah, the magnetic field is in a circular shape. This is the magnetic field. Okay, and it's anti-clockwise directions. How we determine the direction? We use Fleming. We use right hand grip rule to determine the direction. So you just follow how the four fingers twist. It twists in this way, and then the permanent magnet will have that direction. Okay, we use right hand grip rule for straight conductor that carry current. Okay, so yeah, let's see. For a long straight conductor, so you already know, we use right hand grip rule to determine the direction of the magnetic field. And then here, magnetic field lines are concentric circles centered at the conductors. That means they are circular magnetic field. And separation between adjacent field lines increases with distance from the conductor. So as you can see, initially they are nearer, then the distance is getting greater and greater. So initially nearer, then greater and greater. So that is where the separation increases. And magnetic field is non-uniform. Of course, it's non-uniform. That means when it's near to the conductor, it is strong. When it's further away from the conductor, it is weak. So this is non-uniform. Okay, so let's move on. Okay, so on the second page, we can see two examples. So the first example is where the current is pointing upwards, and then you use right hand grip rules where your thumb have to point upwards, then the other forefinger you gripped, so you will realize the magnetic field is anti-clockwise. Okay, and this example is where the straight conductor having current that flow downwards. So you have to use your right hand grip rule. You grip the straight conductor, imagine that, grip the straight conductor with the four fingers, and then your thumb have to point downwards. Then you will realize that the forefinger twists in the way that follow clockwise direction, and this is the direction. You can see that clockwise direction. Okay, so this is the top view. Okay, you look at it from top. Look at it from top. For this, the current is coming up. If you look at it from top, that means this should be a dot. This should be a dot. Okay, this should be a dot. So a dot means the current is coming out of the paper. As you can see here, out of the paper. So we use a dot. Okay, so you can use right hand grip rule again, where your thumb have to point to yourself or point out of the paper. Then you will realize the forefinger will twist in a way that is in the anti-clockwise directions. Okay, so for this case, this is the top view of this one. So imagine if you look at it from top, right? Let's say this is your eyes. You look at it from top, you will find that the current is going down. So this is the top view. What happens is you will see the current going into the paper. If you look at it from top, it's going down. That is going into the paper if you see in this way from the top. Okay, so and we represent it by using a cross. And then when you use right hand grip rule to determine the direction of the magnetic field, so you have to make your thumb pointing into the paper, then the forefinger will twist in the way that is in the clockwise directions. Okay, so the conclusion is, for straight conductor with current, we always use right hand grip rule to determine the direction of the magnetic field. Okay, that is the first situation. Now, our conductor is not always straight, so sometimes it can be this situation. It is a flat circular coil. For a flat circular coil, this is the situation. The current flow up, turning one round, and then flow down again. Okay, so it's a flat circular coil. So the magnetic field pattern produced represents that produced by a short bar magnet. What is meant by short bar magnet? So imagine short bar magnet will be like this. Let's say you have a bar magnet or a permanent magnet. Okay, something like this. This is a short bar magnet. Okay, so as you can see, the direction is going there, right? So that means north is here. Okay, let me write down. Here is the north, and here is the south. So north is here, south is here. Okay, so it's pointing outwards from the north and pointing inward from the south. So what they are saying here is, if you put your conductor in a coil, in a flat coil, so it seems like they form a magnetic field that is similar to a bar magnet in this particular way. So where here is north pole and the bottom here is south pole. So here same, south, north. Okay. So this is a flat circular coil. Okay, so a flat circular coil is one round. Okay, now next one. Of course, again, you can use right hand grip rule, So let's say, for example, this side. This side, the current is going up. The current turn one round and here go down. So here go up. So you use your right hand grip rule. You make your thumb point upwards. Then you will realize the forefinger twist in a way that is in anti-clockwise direction. Now you use right hand grip rule for this side, where your thumb have to point downwards. Then the four fingers will twist in a way that is in the clockwise direction. So as you can see, this direction is clockwise direction. So when something like that happens, then you will realize the magnetic field is formed based on the right hand grip rule. So we can understand that in this way. Okay, so this is everything about circular coil. Now we look at the next one. For a solenoid and flat circular coil. Okay, so what is that? Solenoid means they turn many rounds. Okay, they turn many rounds. So let's look at the picture first. So okay, on the right hand side, this is the solenoid. So they turn many rounds. Okay, we call it solenoid coil. Compared to just now is one round only. They turn one round. Now they turn many rounds. Okay, so of course when they turn many rounds, the electromagnet is a stronger electromagnet. If you put a soft iron core in the middle, of course it is much more stronger. Okay, so that's the difference. Okay, now let's continue with the information here. Okay, so the first point, magnetic field pattern produced identical to that produced by a bar magnet. Of course, it will be the same because this one is already somehow like a bar magnet, and solenoid, of course, will be similar. Okay, let's take a look at the picture first, how it looks like a bar magnet. So it is something like this. It's a bar magnet. Here north and here south. So it is something like this. A bar magnet. The solenoid form an electromagnet that has a magnetic field similar to a bar magnet. So this is the North Pole. Okay. If you are wondering how to determine here is North Pole and here is South Pole, so the idea is right hand grip rule again. Right hand grip rule. So we always use right hand grip rule until all the way until here. We are still using right hand grip rule. Okay, how to use it? So let's say current in. Okay, then we put it in this way. When the coil is turning in this way, so you will realize that the front part is where the current go up, the back is where the current go down. Okay, so I put in blue color for down. Going down is at the back of the, imagine the cylinder, going back at the back of the cylinder, and going in front at the front part of the cylinder. Okay, so what we need to do is we have to use right hand grip rule in a slightly different way. As you can see here, the four fingers is now represent how the current flow. You know, previously is the other way around. Previously, the thumb point to the direction of the current, if it's straight conductor or circular coil. Okay, then the thumb represent the direction of the current. The four fingers represent the magnetic field. But now it's the other way around. Now the four fingers for solenoid, the four fingers represent the direction of the current. As you can see, the front part is pointing up, same like what I said. The back is where it point down. Then your thumb is to the left. So your thumb point to the north direction. Okay, so that's why here is north, the other side is south. Okay, so we use right hand grip rule, but the forefinger represent current, the thumb represent north. Okay, so it is different already. So make sure you know about that. And let's see what else. Okay, we look at the point here again. Magnetic field pattern produced identical to that produced by a bar magnet. Magnetic field lines within solenoids are parallel, indicating strength is same, uniform field. Okay, so where? That means here, let's take a look at the picture. Okay, here, as you can see inside the coil, they are having same distance apart. You can see the line are same distance apart. So meaning that it is a uniform field, same strength. The magnetic field strength is the same inside the coil. Outside the coil, of course, is different. It's non-uniform field. But inside the coil is uniform field. Outside the coil is very easy. When it's near to the coil, it is strong. When it's far away from the coil, it is weak. So non-uniform field. Okay. 9.4 we also discussed already. We use right hand grip rule in that particular way. Okay, so settle for the first two pages.